All right, so um, class 8 was cancelled. It was a snow day. Class 9, the activity packet was modified to accommodate some material from class 8, and of course, there was material from class 9. So, class 9 was the first time you saw something called law of inertia. I want to remind you what that was, and if you remember this, so this is a track, right? And it is elevated from one end, so it makes a ramp. You let go of the ball here, and as soon as the ball will get out of the ramp, it will hit a yellow plastic wall. Okay, so the idea is let's just see what happens first. Maybe I should start with this one first. Oops, oh, not that one. This one. Look, boom, boom. So what do we see? There are two There are two plastic balls. One is right here and the other is right here. Um, um, this is the second one on your screen right now. The ball is the first one, and this is the first one, right? So the ball really, like this is the observation here, and this is how it connects to Newton's first law. The ball really wants to just go in a straight line. Okay, the ball really wants to travel in a straight line unless it is acted upon by an external agent, okay, and that external agent in this case is this wall. So it really wants to go in a straight line, but it hits the wall, changes the direction, and then it again hits the wall and changes the direction again. So I'm going to replay this video real quick for you. First hit, second hit, first change, and then the second change. So that's the uh, um, that's law of inertia. It really wants to go in a straight line, uh, but unless it is acted upon by an external agent. So law of inertia is not just all about this just not all about things moving in a straight line. Okay, it is also about things moving and not moving at all. So if you have a ball that's just sitting there, it is going to really work hard to keep itself there. Okay, unless you give it a little nudge or you try to move it. Okay, so if things are moving, they would want to be moving, and if things are at rest, they would want to be at rest. So that's the law of inertia. Just so that we can complete the discussion, I'm going to show you one more time this third one, the second one, sorry. Oh, such a random. Maybe this one. All right. Okay. So this was the exercise where you guys were trying to have the ball go in an S direction by just moving, just by just moving, just using. What's happening here, as you can see, ball hits this part of this what is that, plastic wall, but as it hits there, in order to have that ball go in S, you need another plastic wall like the video that you saw earlier. But if you have just S ball, like that is not going to happen. It just hits the wall and goes in a straight line. As the ball goes in a straight line, that's it. So things will really want to move in a straight line if they're moving in a straight line already. If they're already in motion, they would want to be in motion. If they are already at rest, they would want to be at rest. Okay. If you have you ever seen a ball that is at rest and suddenly starts to move? No, right? It's not going to start to move if you just let it sit. Unless there's some wind or someone hits on it or something like that. So that's Newton's first law. It's law of inertia, and this property of objects to not really to be hesitant to change their state of motion is called inertia. Okay, so that's Newton's first law. Then we encountered in this lab something called law of interaction, or Newton's third law. We skipped Newton's second law for the next lab. For but no law of interaction has to do with interaction. Okay, I'm sitting right now in this chair. The idea is my weight is pushing down on the chair, and the chair is pushing up on me by the same force which is equal to the weight, right? So if I really want to write down in a sentence, I will say for for an action there is an equal and opposite reaction. For every action, I should say, for every action, there is equal and opposite reaction. Okay. Now, for this case, it was I'm tugging on this wire to the right. My left hand is tugging on this wire to the left. So that's what law of interaction is. When you're sitting in a chair, your weight is being pushed into the chair. The chair pushes up on your weight and by the equal amount. So that's law of interaction when it comes to that's law of interaction when it comes to an example of sitting in a chair. The third thing that we talked about, like I mean, there are a bunch of other things as well, I think, but the third important thing that I want to talk about right now was inferring things like when the velocity is constant, when the velocity is increasing, and when the velocity when the velocity is zero, for example, from a distance time graph. Okay, so we all know. I'm going to first start with the formula of velocity. So velocity is equal to distance over time, right? Just remember that. I'll come back to that. Distance over time. All right, we're good. Um, so if you have a distance time graph, time on the right, on the x-axis, distance on the y-axis. Okay. If the velocity is constant, then you will see that distance time graph will have lines like this. All right. So that means that the velocity during that time, like during this time for this curve, like this time for this curve, and this time for this curve. So whenever the lines are straight, that means that the velocity is constant, okay, in a distance time graph, because velocity is given by slope, which is of rise over run, right? So if the rise over run, the ratio of rise over run it stays the same, then you see something of a straight line in a distance time graph. And I said that I will connect that back to the formula of velocity, and the way you connect it is velocity is the slope of the distance time graph. Okay, that means distance here, time here. Okay, now you can imagine if we are talking for about a case where, let's say I'm gonna make the graph one more time, not the same graph, but the axis the same. So let's say if the velocity is changing. Oh, before that, I should mention here is that, and that's, this is a constant velocity. This is also a constant velocity, and this is also a constant velocity. But because this is steeper, the velocity here is more as compared to here, and this velocity is more as compared to here. So the larger the angle it makes with the x-axis, the larger the velocity is. If the angle is like this, right, which is 0 from the x-axis, then the velocity is negative. Or if everything else is moving this way, then for this case, it is moving, the particle, the mass is moving that way, right? That is what we mean when we say velocity is negative. That means we have assigned a positive direction and the velocity is in the negative direction of that. So that's why when the slope is negative, the velocity is also negative. But you can imagine a case where the velocity is changing, or let's say the velocity is increasing. Okay, so the velocity is increasing. That means there is something called acceleration. All right, you're at the red light, so your car is stopped. Right, then you see it's green, so you push on the gas pedal and you begin to accelerate. So when you begin to accelerate, you start to acquire velocity. So your speedometer, it goes up and up. So you start from 0 miles per hour to 15 and 20, and if you push on the gas pedal more, it will continue increasing. All right, and if you maintain the gas pedal at a particular particular pressure, the velocity remains same. So that first bit, when you started from the rest, what you were doing, you were accelerating, or in other words, you were increasing the velocity of your vehicle over time. So what that means is that over time, this steepness should increase, right? Because we just agreed on the fact that the steeper a constant curve is, the higher the velocity is for that one. And remember, when they make straight lines, this is a case of constant velocity. Now we know this: the steeper the curve is in a distance time graph, the higher the velocity is. And that means that if, let's say, I start from a case where let's say the velocity was something, let's say something, some velocity, right? Let's say some velocity, right? Some constant velocity, and this is that time up to which the velocity was constant. But um, now the vehicle is, let's say the example of vehicle, the person who's driving the vehicle pushes on the gas pedal, so they really want to accelerate. So they were traveling at, let's say, 15 miles an hour, but they want to go at 60 miles per hour. So what that looks like in graph is the angle increases, right? This is how it will look like. So when you have this going on, where instead of a straight line like this, the angle of the curve increases like that, then you have a case of acceleration where the velocity is increasing. Okay, so that's the difference. When you have a case, let me discuss the very last thing as well. When you have a case where it is not like this, it is not like this, and it is also not like this, and it is also not like this. That's the case of constant acceleration, right? Kind of acceleration, that is velocity increasing. But you have a case of this, right? Let me make that. We have a case of this. So this is a case of the car slowing down because the angle is getting less and less. So what that is means that it is acceleration, but in the negative direction, or you can also call deaccelerating. So when you're moving at constant speed and you push on the brake pedal, then this is what happens. So you deaccelerate.